Hello, everybody. Welcome to our webinar, the last on the Greener ATM series. That's dedicated to the en route domain. My name is Olivia Nunes. I have been working for the SJU for 8 years, and I have an operational background. I've been a controller before that for about 20 years. And before getting into the topic, I just want to remind you, this is the last of our 2020 series of webinars. All the other webinars are available, both recording slides and questions and answers on the SJU past events page, which is on the SJU website. So without further ado, just a comment on the housekeeping. This is the Livestorm tool. We have both a chat and a questions tab. So you can chat away in the chat as much as you like. We are unable to monitor the chat. For any questions, please go on to the questions. And we will be aiming at answering as many questions as possible. We want to make this as interactive as possible. We like questions. So please, there are no silly questions. Just go ahead and ask away whatever you want to ask. And we will answer them either live if we can, or if not, then they will be answered afterwards. So quickly, today's speakers, we have 4 themes. The first one is free routing APA airspace. The second one is civil-military cooperation. And the third one, we're going to talk about contrails and more about non-CO2 impact of aviation on the climate. And last but not least, we have wake energy retrieval. And then at the very end, we're going to have an overview of the key takeaways and next steps, just summarizing what has been these Greener ATM Solutions webinars. So without further ado, we're going to go into our first presentation. Sorry, I have a problem with my mouse. It doesn't seem to allow me to stop sharing. Let's. Can someone please? Thank you very much. So our first speaker is Florence. She has been an ATCO for 30 years when she joined DSNA, and she has been involved in many projects for various aspects of improvement of ATM operations, and in SESAR specifically since the year 2010. She is the lead in the SESAR 2020 trajectory-based free routing 2V3 project, which brought the free route in high density, high complexity to V3 in 2019. Florence, the floor is yours.
Thank you, Olivia. I try to share my screen. It worked just before, so it should work. Sorry for that. Well, it seems that it's not possible for me to share my screen. It worked just a couple of minutes ago.
I have recovered my mouse.
Yeah.
So if you want to,
maybe
I can share. Do you want? I have your slides. Do you want me to share your slides?
Otherwise, Florence, what you can do is just to get out and click on the link again.
No, I think it works now.
Perfect.
Okay.
We can see it.
Yeah, I think it works now. Okay, so sorry for that. Yeah, as kindly introduced by Olivia, my name is Florence, and I work for the SNA, and I led the SESAR 2020 free route project about free routing in upper airspace high and very high density environments. Well, I'm pleased to present this project to you today. First of all, before we start a quick recap about what is free route airspace. So a free route airspace is a specified airspace within which users may freely plan a route between a defined entry point and a defined exit point, with the possibility to route via intermediate published or unpublished waypoints, and without reference to the ATS route network. Free route airspace is a controlled airspace, generally of class C, and for sure subject to airspace availability. So as you understand, free route concept is about flight optimization. Indeed, it allows airspace user to plan a route that is as close as possible to their preferred trajectory. And so as the planned flight is optimized, the quantity of fuel that is embarked is optimized too. But on the other hand, free route operations might be a bit difficult to manage by the ATCOs because they lose the benefits of a fixed route network, and so might be a bit trickier in terms of conflict detections and resolution. As part of SESAR 2020 Wave 1, we delivered a SESAR solution ready to move towards industrialization and deployments. And the solution was about optimized traffic management to enable free routing in cross-border, high and very high complexity environment in upper airspace, and supported by ATS system improvements, namely flight data processing systems and controller support tools. In order to validate the solution concept, we performed real-time simulations on a simulator in Madrid and Geneva. And for the sake of these exercises, we defined free route airspace, cross-border free route airspace in Spanish airspace, Madrid-Barcelona, as well as free route airspace in Switzerland and in Italy. And by the way, just after my presentation, Max Canham from Skyguide will present how this work fed the Skyguide free route airspace deployment project. So what about the results? First of all, you understand that free route concept is really permissive in terms of flight planning options. So as we were in high complexity cross-border environment, the objective was not to target unrestricted free routing operations, but we aim at enabling self and efficient operation in free route airspace, supported by ATC tools and with minimum structural limits to manage traffic complexity while maintaining, and this is for sure the most important part, while maintaining not only the safety, but also the capacity of the airspace. So the validation exercises results indeed demonstrated that when an adequate infrastructure is put in place and the tools are available for the ATCOs, no negative effects on airspace capacity and safety were observed. We measured also an improvement in flight efficiency The figures we got are 27 kilogram less of fuel burned per flight concerned by the solution. So this is an extrapolation of the results at horizon 2035 for all ACCs in ECAC of high and very high complexity environment. So this means fuel saving of about 245 billion tons per year. So it means also reduced CO2 emissions. Once again, the figures we got were about 84 kilogram less CO2 emission per flight, and so per year of 772 billion tons of CO2 per year. We also expect for these operations improved predictability with less trajectory revision needed during flight due to the optimized trajectory at flight planning level. We performed also a cost benefits analysis at the end of the project. So the cost benefits analysis was performed at horizon 2040 and at ECAC level. And we demonstrated a positive NPV of 797 billion euros with a payback period of 5 years after commissioning. It is to be noted that these studies have been performed before the COVID-19 crisis. So the figures might need to be a bit revisited now. To finish with, I would add that all the deliverables constituting the solutions data pack are available on Cordis through the European Open Data Portal. So Max, now the floor is yours to present the skyguide free route airspace program, and I will just stop sharing my screen.
So hello, Max. Sorry, I didn't introduce Max before. Max is actually, like Florence was saying, working on the follow-up of this. So his background is he was an en route air traffic controller in Australia. He had some various roles, supervisory training, safety management in the safety department. And he joined skyguide in 2007 as an operations safety manager. And from 2010, he's skyguide's manager at the FABEC Airspace program. And a few years as head of Airspace and PANSOPS also at skyguide. So he has a very operational, safety-oriented background. And he is now managing various operations, development, and implementation. And in particular, he is leading now this free route implementation that's following up from the SESAR validations. Max, the floor is yours.
Thank you very much. I don't really need to make much of an introduction. I am here to talk about how skyguide used the results of the SESAR project. We participated inside the SESAR project, and how we use this and how we're still using this as we move towards implementing our free route airspace. So I'll start with a little bit of a history lesson. According to the Pilot Common Project legislation, the ATM functionality 3, which is inside their part 1, we needed to implement a direct route airspace. And within skyguide, we had a project team working on this, and this project team was running towards the end of 2018, getting towards the end of the project, and they were looking to set up a free route airspace project and how we were going to implement free route airspace within the skyguide managed airspace. So this was part 2 of the ATM functionality 3. And while we were setting this project up, we had a look around the organization at what was being done in skyguide at the time. And skyguide was participating to the SESAR PJ06 project, which Florence just covered. We had a project team led by Olivia Hewitt running this, and we were planning to run inside this quite some live simulations with 4 Zurich sectors and 4 Geneva sectors, and about 30 ATCOs participating to these simulations. We also had running a skyguide at the time, a virtual centre program. This is a technological involvement program inside skyguide. It's looking at changing a lot of different things, and this has been presented before in some of these webinars. But the main element that we were interested in, or setting up the FRA project, is that the technological program inside the virtual centre and the FDP developments and the changes to the tools that the ATCOs are using. So while we were setting up the FRA project and looking around at these, we also noticed that inside the SESAR project, we had air traffic controllers who had been participating in our direct route airspace project. From a virtual centre program, we had an overlap between the human factors, the safety people, and some of the technical people. So a decision was made at the time that that inside the SESAR project, we would develop the two key parts of our FRA project within the SESAR simulations. So this is the FRA design, the airspace design for what the free route airspace would look like. Florence mentioned it'll be structurally limited and complex airspace, and we had a lot of simulations running, so we were confident that we would be able to take away a design to implement inside the skyguide area, and also to look at the technical requirements that were needed to support the air traffic controllers. At the same time, I was appointed as the project leader for the implementation, so I worked quite closely with the SESAR project, and there was quite an overlap between the controllers, the people involved, what they were doing, what I was doing. And at the end of the SESAR work, we were lucky enough to be able to take the air traffic controllers, as well as you know, some of the human factors and safety experts back into my team, and as well as a validated free route airspace design concept. So this is what we're working towards implementing. And at the same time, the technical requirements were then embedded into the virtual centre program, and there's two key elements which are needed for skyguide to be able to operate our FRA correctly. These are called internally to skyguide and new route handling. This is the way that the route or the flight data processor extracts and displays the route to the air traffic controller. And also an exit conflict detection tool, which needs to be modified to operate into the free route airspace concept. And this is displaying conflicts to the air traffic controller about the exit conditions and how the aircraft are being transferred to other sectors. These requirements have been put inside the virtual centre program and will be delivered by this program separately and then away from the actual free route airspace program that we're running. So this gave us quite some benefits. Obviously, we were able to set up a very lean free route airspace project because there's no major design or technical elements. The design, the core elements of the design were taken out of the SESAR work that we were involved with. And the technical elements were embedded into an existing technical program, which was also running. And we also had, you know, one of the big benefits here is we have a continuity of personnel through. We've had air traffic controllers who are still working inside the project who were working back on the direct routing airspace project in 2016-17. We've got human factors experts who were involved in writing some of the documentation for the SESAR who are still working inside my project. So this is really beneficial for skyguide on how this is set up as well. We also get quite some other benefits outside of these elements, and the SESAR work that has been done and delivered. Florence mentioned before that there's a package of work available on the website. One of those things which is useful for me as being in charge of the implementation is there is a safety assessment report available in the SESAR solution documentation. This is obviously something which helps me to make sure that the safety work that we do for the implementation is in line with that document. And it's also something which, you know, is something I can provide to our NSA as part of the implementation package. The other thing is the validation data. Like I said earlier, we ran some simulations. There was 2 separate weeks of simulations, so more than 2 weeks of simulation here with a lot of air traffic controllers. And you can see in the graph here that the green lines are the reference scenario. So this is the today situation. And the other lines are the different FRA scenarios which were tested in the simulation. And you can see the results here from the exit questionnaires and the sampling which was done in the simulation. This validation data is also providing a really good baseline for us to be able to explain to our NSA why the design that we are implementing will be safe when it is implemented. Another benefit, other than just the continuity of people inside the project, is the continuity of the relationships. One of the two of the key elements in here is the Eurocontrol network management team. They participated in the SESAR work here. They monitored the design that was being done within the SESAR. They provided a lot of data support and flight plan development support for the simulations. Those same personnel that were working in the SESAR work are now working with me for the actual implementation. So we have quite some consistency and a good relationship with the Eurocontrol network manager because of this. And also the surrounding ANSPs. Italy was involved, DSNA was involved, and these people have seen some of the design that is there, or seen the core design, and makes the discussions and the things we need to do for the implementation easier to discuss with them because they've been part of it for quite some time. We also get an understanding from the simulations, especially particularly the access to the air traffic controllers and their opinions and the questionnaires that they answered. On top of the measured data, we know that we need to do some things with the ATC procedures. We need to make it very clear in the letters of agreement what the transfer conditions are. Obviously, in a free route airspace, you've got more routing options and more ability to cross boundaries in perhaps different places. So the letters of agreement need to clearly specify what the conditions for the transfer are. This is also linked to the exit conflict detection tool that I was talking about earlier that will be developed or delivered in the technical program. And also the handover procedures have to be clear for all actors. We have to make sure that not only are the conditions for the transfer clear, but also who is responsible for different parts of the separation. And finally, we get a lot of detailed information from the simulations that we need to consider when we're developing the training package when we're going to implement this. Obviously, the ADCO training is something that we need to consider for the implementation, and a couple of key takeaways that we've taken out of the simulation work is the higher variability of trajectories in a FRA environment. Even though it's a structurally limited environment, we are allowing a lot more route connection options that you would have. And this provides a different number of trajectories and a different conflict pattern. And on the top right-hand side of the slide, you can see two pictures with some red lines. The left-hand picture shows the conflicts in the today's scenario, in a route structure scenario. And on the right-hand side, you see the conflicts in a free route environment. You can see clearly that the conflicts are split out a lot more in the airspace, and this is something that we need to explain to the controllers and make sure that they have some exposure to before the implementation. And the other element is on the bottom right-hand side of the slide, you see a picture of the FRA design. You see there's a lot of straight lines between the entry to the airspace and the exit of the airspace, and there are not many, for the size of the Swiss airspace being quite small, there are not many waypoints in between. The lines being straight as well, with no curves in them, means that it's a change to the way that the air traffic controllers need to do their job. Normally, they can solve a lot of conflicts by offering a direct to a waypoint. And say you're re-cleared to this waypoint, which will take the aircraft out of the conflict. But with no waypoints to send them direct to, there is a change to the working methods here and potentially the need to do a little bit more vectoring. So these elements are also coming out of the validation reports from the SESAR work, and there's still information which I'm using as part of the implementation program. So that's it. It's an overview of the key information that we've been, or skyguide has benefited from being part of the SESAR project that Florence introduced.
Sorry, Olivia, I do not hear you.
So my apologies. Thank you very much for both of you for the presentations. And I think it's very interesting that both of you agreed to come today so that we can see actually this continuum from our validations and onto the implementation. There are a few questions coming up. I know that I think some have already been answered. You may want to take a look. And then for the time being, we're going to move on to our next presentation. We're going into the civil military topic. So maybe I can ask Remus to come on stage, please. Hello, Remus. So hello, for the civil military, as you can imagine, we need both civil and military. So we actually have two people here. We have Remus and Yevgen. But unfortunately, Yevgen is having a connectivity problem. And so it will be only Remus presenting. Remus is currently a senior ATM expert for civil military ATM coordination, and his background is as a military air traffic and air defense control. And also He has participated in the NATO Joint Air and Space Power Operations, and he has worked in SESAR 2020 Wave 1, our previous wave, in the projects 8.1 and also 19.4, which is our performance analysis. And currently he is working in Wave 2 in the solution 40, which is management of mission trajectories with integrated DMAs, dynamic mobile areas. So Yevgen, who is not presenting, is working very closely with Remus, and he has a civilian ATCO background. He has been a controller, and that's why he was with Remus supporting. He's there, but I think he has a problem with the audio, and that's why it will be Remus presenting for both of them. He was actually the solution lead for both solutions 8.1 and 8.2. And he is currently the leader of this dynamic airspace configuration sources development. So welcome to both of you. And Remus, the floor is yours.
So thank you, Olivia, for your introduction, and good afternoon to everybody. I hope you are seeing my screen and you are hearing me well.
Everything okay, but I'm not sure if it's the first slide. Yeah, there we are. That's the title.
Okay, so as mentioned by Olivia, I will present you an operational solution that reached a quite good level of maturity in SESAR Wave 1 project 0801, which was handling the advanced airspace management and more specifically dynamic airspace configuration as part of development and implementation of the advanced flexible use of airspace concept. This solution, which indeed as presented is about new principles for airspace reservation and restriction definition and demand, is about dynamic mobile areas. What we have done in SESAR so far was to develop two types of dynamic mobile areas, the type 1 and type 2. And mainly our presentation is built around the achievements we reached in Wave 1 in solution 0801 with regards to the contribution of dynamic mobile areas to a dynamic and flexible configuration of airspace structures, and eventually to the contribution of this operational concept to greener on-route ATM operations. I'm very happy that my presentations comes after that one linked to FRA, because there is a logical connection between what we do in the military environment and what is the civil needs in terms of efficient usage of airspace. Before reaching the conclusions of SESAR 2020 Wave 1, I will just give you a short insight on why we need civil-military ATM coordination, what is the guiding principle, and what we have done in SESAR 2020 Wave 1. So, as acknowledged by the Single European Sky Initiative and SESAR, civil-military ATM cooperation and coordination is a key enabler to building what we call an integrated civil and military ATM environment for the target of 2035 in the European ATM environment. The guiding principle, the global principle of ICAO, which is guiding the civil-military ATM coordination, is the flexible use of airspace, according to which the airspace shall not be designated as purely civil or military, has to be seen as a continuum with the ability to accommodate to the greatest possible extent both civil and military requirements. This was the initial principle of FRA, to which with the evolution we added a second one, which is about balancing the economic needs of civil aviation with the security and defense requirements of military through collaborative decision making. Those are two principles of flexible use of airspace, and also two principles which are guiding the development of the dynamic mobile areas operational concept. What we have done in SESAR was to try to keep the pace with the forecasted evolutions for both civil and military requirements, so that starting with from the basic situation, which is, however, visible even today, in which the civil aviation was able to cross areas reserved for military purposes only when they were released by the military stakeholders and based on some conditionalities, the so-called conditional routes. We succeeded to deliver in SESAR 1 new design principles and management methods for airspace reservation restrictions, which is about the variable profile areas type of reservation, which basically means that an airspace volume designed for segregation from the other traffic is split into basic modules, predefined basic modules, which are allocated and planned for reservation or restriction as close as possible to the actual needs of the user, and in this way enabling also consideration onto the civil traffic demands. Finally, in SESAR 2020, both Wave 1 and Wave 2, we are addressing the concept of dynamic mobile areas, which is an evolution towards the possibility to define airspace reservation or restrictions in an ad hoc manner and to allocate them throughout dynamic and flexible planning processes. So this, in the end, should support a full implementation of the free route area operations into the European air traffic management. So what is the dynamic mobile area operational concept at a glance? So this is about the possibility, once again, to define ad hoc an airspace volume for reservation or restrictions by taking into account available information on civil traffic demand, and by allocating this airspace to the user throughout a civil-military collaborative decision-making process that is based on integrated information concerning the requirements of airspace management, concerning the requirements of air traffic and flow management, demand and capacity balancing, and nevertheless the requirements of air traffic control sectorization. So far, we have succeeded to develop two types of dynamic mobile areas, type 1 and type 2, which are both of them geographically dependent. DMA type 1 is dependent on a specific reference point and respects user mission constraints. The best example of a DMA type 1 area is that one designated for training, basic training purposes of the military, to which the areas should be placed as close as possible to the airfield in order to maximize the time inside the reservation for training. DMA type 1 is not necessarily linked to a trajectory, while DMA type 2 it's always linked to a military mission trajectory and can be placed at a variable geographic location along that trajectory and can be activated or deactivated during specific time frames so that to enable a minimization of its impact on the effectiveness of traffic flows. Usually, we see these DMAs type 1 and 2 as aggregated because according to the military mission requirements, there could be the case that both of them are required to be defined to support the execution of the mission. I would like only to highlight that there is another type of DMA which is currently only in exploratory research, that is the DMA type 3, which is a volume of airspace designed around a moving aircraft and which brings more dynamicity in the management of airspace reservation. But that will come hopefully with the next waves of SESAR. What is the main contribution of DMA to the implementation of flexible use of airspace, and more specifically the advanced flexible use of airspace, is the possibility to configure the airspace structures, meaning here the air traffic control sectors, the airspace reservation and restrictions, the optimized trajectories in a dynamic and flexible way, Flexible means that the user preferences, the civil user preferences and the military operational requirements are fully addressed and taken into account in the planning phase. Then dynamicity means the possibility to adapt the configuration of the airspace structures to the evolving situation of traffic demand. And nevertheless, the balance between civil and military requirements is ensured throughout collaborative decision-making. Key enablers to a dynamic configuration of airspace structure are automation and digitalization. Without automation, it will not be possible to run this kind of dynamic processes for the configuration of airspace structures, and nonetheless, digitalization is the key also to have this kind of effective real-time communication between all the stakeholders engaged. As mentioned, what the DMA brings into this dynamic airspace configuration and what the automation support and digitalization provides is about dynamicity and flexibility. Dynamicity means that the airspace reservation and restriction is enabling and is allowing changes in the dynamics of air traffic demand evolution. The tools we have used in SESAR 2021 provided us with the possibility to identify automatically different positions of the DMA, which could be in different scenarios implemented in order to mainly enable alleviation of traffic flow complexity. Flexibility is present in 3 dimensions. So the DMA is flexible in time, is flexible in geographical location, and is flexible in altitude, meaning that the specific requirement of an user, of the military airspace user in our case, for the duration of a training inside a segregated area, for the location of this area depending on some constraints concerning, by example, the transit time to this area, and also a minimum fly level block to perform the training could be moved horizontally, vertically, and in time within some windows that are predefined by the user. Those windows are integrated into several scenarios. They are simulated, and the tools provide the possibility to measure all the time performance indicators that show the impact of this kind of area reservations on the effectiveness of traffic flows, but also on the workload of air traffic controllers. Now, once again, when coming to the benefits that the DMA could provide to greener en route operations, I would like to highlight once again that what we have done so far in SESAR was about V1 and V2 validation, that in accordance to SESAR methodology means a great focus on proving the feasibility of operational processes and technological support. So what we achieved is about rather some promising results, qualitative assessments, than quantitative measurement of performance indicators. However, we have addressed mainly 3 key performance areas that to lead to a conclusion with regards to the contribution of DMA to greener en route operation needs to be seen in interdependency. So we concluded that by using the DMA allocation principles and methods, we will be able to deliver and to release more airspace for civil traffic planning and usage. This, in the end, leads to a better management of en route capacity. A better management of en route capacity will ultimately lead to a reduction in route length, to a reduction in flight duration, and consequently could have positive effect on the fuel consumption for the individual flights. Next, when it comes to the key performance area of civil-military cooperation and coordination, which in SESAR is addressing two main threads. First is about what could be the impact of ATM solutions on the effectiveness of military mission, and the second one is about the contribution of civil-military cooperation and coordination to the ATM performance areas. We concluded that by exploiting the DMA concept, there are certain opportunities to reduce the transit times to or from airspace reservation restrictions, which could lead to a better management of fuel consumption for the military stakeholder. DMA could also lead, and this was a clear conclusion coming out from our exercises, to a decrease in the total number of civil flights impacted. Mainly we speak about reroutings here. The number of reroutings was to civil traffic was reduced, and this could lead also to a reduction in the route length, flight duration, and consequently fuel consumption. Next, what I would like also to mention is that we are continuing the development of the concept in the second wave of SESAR 2020, and this will be focused to prove the performance benefits of these operational concepts, and in the end to make it ready for implementation. Initial operational capability is intended to be in place starting with 2027-2029. Before ending my presentation, this is a slide with a pool we propose to you for your discussion. It would be nice if you could answer to these questions, and this is about what you think that should be the priority of civil-military ATM cooperation in order to improve the efficiency of ATM in Europe, and finally to have a positive impact on environment. Could be this about the performance of assets and equipments? Could be this about more flexibility in planning and using the airspace? Is this about an enhanced collaboration between all stakeholders? And here we speak about enhanced collaboration between civil and military. Or finally, could be about interoperability of processes and assets. This brings me to the end of my presentation. Thank you very much.
Thank you very much, Remus, for the very interesting presentation. Everybody, please, we appreciate if you go ahead with the poll. I honestly wouldn't know what to answer. They all look so interesting and so necessary. We're going to move on to our next presentation. Our next presenter is Sigrun Mattes. Sigrun, can you come on stage, please? So Sigrun is a member of the SESAR exploratory research community. She holds a diploma in physics and a PhD in meteorology. She has over 20 years of experience in atmospheric impact modeling studies at DLR in I'm not able to pronounce it. And she's currently coordinating a SESAR project called Fly ATM for E, Fly ATM for the Environment. And she will be presenting results from the predecessor of this project, which is ATM 4E. And they are dealing with eco-efficient trajectories. She's going to be talking to us about the non-CO2 impact of aviation on the climate. Sigrun, please. I think Sigrun may have maybe having a connectivity problem right now.
And he said it was okay. Let me check.
If not, maybe.
I think now it worked.
I think.
All right, perfect.
Really sorry, I had to connect. So some strange reason. Wonderful. So I just heard an introduction, and thank you very much, Olivia, for giving me the possibility to be talking about air traffic for the environment. Do you see my slides already? No, probably. Right?
Not yet.
Yes, here we go. Okay, that looks better. Okay, everything good?
Perfect.
Good. So, and in fact, my topic today is, let's say, climate efficiency beyond CO2. And in fact, we're talking about contrails and more. So what is it? What is motivating the work we are doing? In fact, the climate impact of the aviation emissions is determined by the CO2 emissions, but additionally, there is non-CO2 effects. And among these non-CO2 effects, there are nitrogen oxides, there are contrail cirrus, water vapor, and soot. And in fact, this is what IPCC is talking about. And I always mention as an example the most obvious non-CO2 effect. And in fact, these are the contrails and the contrail cirrus, because you can even see them in the sky. So what is it? How we are measuring? So in terms of the IPCC, the International Panel for the Climate Change, we are talking about the warming effect for the carbon dioxide. But if we go further down here, down the road, we are talking about the NOx-induced effects, which are caused by ozone production, additionally a methane reduction, and which is causing a total effect. And the same is for the water vapor, which is emitted by aviation if it flies at high altitudes in very dry regions. So that's additionally warming the atmosphere. And we come also, I want to draw your attention to the linear and contrail cirrus, which are also warming the atmosphere. So in fact, there is a same order of magnitudes as non-CO2 effects than the CO2 effects. And in fact, the same example for the contrails, the climate impact of these non-CO2 emissions depends very much on the time and position of the aircraft, on the actual weather conditions, and on the background conditions. So typically on some days you see the contrails, while on others there are no contrails formed at all because they just dry out. So in fact, a climate optimized trajectory tries to avoid such sensitive regions. And this is in fact the approach that is kind of undertaking when you aim to optimize for climate. So we have currently the situation that there are assessment methods how to assess the environmental impact of aviation, and it's not only on the climate, but it's also air quality and noise. Normally you do it offline. That means once the aircraft has flown, you are calculating what are the impacts to it. However, the idea that we were following on in this exploratory project ATM4E was to make such information available during the trajectory planning process. So the idea is to really provide information on the impacts to the planning tool. And we propose to have such integration of these additional information via a kind of metadata. So the metrology is available, and additionally, the idea is to provide the impact on climate, the impact on air quality, and the impact in terms of noise. And in fact, ATM4E was aiming for the first time to try to identify then trajectories which avoid those, if you see here, those red regions, by flying more to the green region. Of course, that's a sketch. So flying through the green regions in order to identify trajectories which are lower in their impacts. And then if you have it in your planning tool, you can see how the overall performance is. So this project aimed for having a feasibility study for flying such alternative trajectories. And the idea in it was to have it really multidimensional and multi-criteria optimization, which means beyond the costs, beyond the time, you are adding additional information on the environmental performance. And this was a collaborative project, which we did in the second wave of the exploratory research projects. And the question is, how do we establish such interfaces? How do we come from climate science to such interface information? And in fact, here we are a bit illustrating how it looks like. This is a sketch of the North Atlantic Flight Corridor. This is US, this is Europe, and this is in fact 2 locations where aircraft could emit. And what you see here is the meteor. So what is then done in our models with a Lagrangian approach? We are studying how such emissions kind of, what is happening if you emit. And what you see is in this situation, okay, it's, what you can see is if you emit here, the air parcel is transported downward, so it's losing altitude. While here, it's only briefly losing altitude and then being transported up, and it goes to the tropics. And this is by the color coding, this is where we are indicating the formation of the ozone. And you see that in the tropical latitudes, these air masses, they are having a very efficient photochemistry. So in fact, during the days after the emission, there is efficient photochemical ozone production. And these are 2 individual trajectories. Of course, in a Lagrangian approach, you calculate lots and lots of them. This is just to illustrate that depending where the air trajectory is driven, there's either an efficient ozone production or a much less efficient. And such information is then translated to this kind of weather chart, which would mean the flight planner gets an additional information, not only the meteor, not on the location of the jet stream, but he would also get the information that in fact here there is low impacts, while on the east of the Atlantic there is high impacts. And the idea, which was exploited in this ATM4E project, was to have such weather charts on the impacts derived directly from the meteorological data. So we were working on establishing such an interface. And in fact, this is where we established the concept of having those algorithmic environmental change functions. Algorithmic because in fact, it's a mathematical function, which is based on humidity, temperature, vorticity of the atmosphere. So this is normally what a weather forecast model can tell you. And then it allows you with such meteorological data to generate these change functions and give it to the air traffic optimization. The idea is, of course, to integrate such environmental impact information in a kind of infrastructure, making it available to all the planning tools. In fact, how would it look like? So the idea is you have the atmosphere, you have the different cost functions, you have the different geographically resolved information on the individual impacts, and then you give it to the planning tool. When we come to meteorology, we also have to recognize that for the time being, there is no perfect forecast for the next day. So there are different realizations, which are sketched here by this kind of uncertainty range. So depending on the next day, with a certain probability, there's a forecast. So we are currently exploring if our forecasts are robust, if we can provide a robust recommendation where an aircraft has a low impact and where it has a high impact. And in fact, this is where we are using probabilistic data for the next day and translating this to again to the cost functional, which allows then to assess if we have robust solutions, because we understand it's our idea is it's important that no matter how the real weather will be showing up, your planning tool has to provide a robust recommendation where to fly. And in fact, this is a question which we are currently exploring in a follow-up project, which just started this summer. And in fact, this is Fly ATM4E. And for the Fly ATM4E project, we are exploring robustness. When we did a one-day case study, in fact, we were doing a case study for a specific day. We said, okay, how would it look like if we try to have all the flights over Europe optimized, either fuel optimal or climate optimal? and what would be the individual changes to the trajectory, how much can you gain? And in fact, this is where we just published a study recently where we selected a day with a high contrail formation, okay? Because this is when it's kind of getting interesting. If you have something blocking in your way, this is when you see, is there a way to fly around, to fly below? What are the alternative routes? And we did a winter situation for 2018 for one-day traffic. And in fact, what we found, and we did the analysis for the whole day, but I'm showing you here two different trajectories. This is a trajectory which is kind of blocked with a contrail forming region, which is spreading over the Central Europe here. And you do a very small change in the trajectory, which is only 0.5%, less than 0.5% of the fuel. And you can mitigate the full contrail impact because the aircraft can simply fly below. So with a shallow dive in the trajectory, you can avoid that region. If there are no such blocking regions, then you are mitigating on the NOx-induced climate impact. This is when it goes a bit slower. It's not that, let's say, that easy or not that efficient to mitigate, but you can also gain on the NOx because this is when you see that the total effects are also going down. So in fact, we studied this kind of case study and feasibility study for Europe, and we felt one needs to explore it really to a full European scale application. One should exploit to what extent we can also measure the benefits by having powerful performance indicator. Because we think if you're not able to prove the benefits, you would never be flying such a trajectory. So it will be important that the performance indicators are able to capture your benefit for the environment. So this is what is currently also underway. And second, this is the idea which I already explained a bit, the robustness. We felt it's very important because we don't want to give wrong incentives. We don't want to give the systems should be able to have a robust recommendation even under uncertainty, and this is what is currently explored. So we are here, this robustness issue, this is really to try to identify such a concept which enables robust and eco-efficient reduction in the aviation climate impact. As I mentioned, we just started. We will be running for the next 2 years, so we hope to be kind of coming to more experience on these two important topics. And additionally, we are also aware that specific weather situations, and I'm coming back again to these contrails, in specific weather situations, there is a larger mitigation potential. And it can be beneficial in order to start with to identify those weather situations where you can have easy wins, where you can have easy benefits, and then trying to start implementing an optimization on these days. So this would be a kind of cherry picking approach and a win-win situation, making sure we are doing initial steps for the optimization. Don't let me forget to mention one thing. We are currently working on having these aECFS, these algorithmic climate change functions. We have prototypes of them. We are continuously updating them, and we're also in direct contact with weather services because we want to make sure they have a really good quality and they will develop to a quality which will enable to have a reliable forecast. So that's still under investigation, but for the feasibility studies, we are working with prototypes. So beyond the Fly ATM4E project, I also want to draw your attention a bit to other projects to conclude my presentation, because there's also other projects which will deal with the topic. So Fly ATM for the next 2 years, we will be up and running. There's also DINCUT, which is focusing on the TMA area. And then there is also aeronautics project, because being very clear, the scientific understanding, there's still open question, and there's still the whole climate community which is still working on understanding the individual impacts, and we are also involved in working together with them in order to make sure that we can propose operational improvements for the benefit of environment and in particular climate impact. So with this, I would like to thank you for your attention.
Thank you very much, Sigrun. That was a really interesting presentation. I already answered one question because I thought I could. You may want to take a look and complement my answer. And I think we may be having more questions coming up. Now we're going to move on to our next and last presentation from Nick McDonald from Airbus. Can you, Nick, please come on stage? So, all right, perfect, because Nick had a connectivity problem. We've had a lot of technical issues today. So now I see you're successfully there. Perfect. So I was going to say Nick has worked for Airbus for 18 years. He has worked both in the UK and Singapore. He has always worked in the engineering department, sometimes R&D, also customer service. And he is currently the lead of the FRA Project. And that's what he's going to be talking to us about today. Nick, please, the floor is yours.
Okay, thank you, Olivia, and thank you for the invitation to join this SESAR Digital Academy. So just following on actually from Sigrun's presentation on the environment, well, Wake Energy Retrieval is also a project that's very much focused on the environment. And really to start speaking about the environment, well, where better than nature, in fact, because Fellowfly is a project that's very much inspired by nature. And you can see on the screen a picture of these kind of large migratory birds that fly in this kind of characteristic V shape. And scientists have found over recent decades that the reason they do this, in fact, is because they're flapping their wings to follow the air that's displaced by the bird in front. So what they're basically doing, if you like, is surfing this air that's displaced by the bird in front in order to save energy over long migrations, often intercontinental migrations. Okay, so it's pretty incredible how nature continues to inspire us. So Wake Energy Retrieval is actually a similar principle, in fact. So following on from migratory geese, there's been a number of studies done, particularly in the academic circle, about how a similar principle could be used for commercial aircraft. So you can see on the screen here, every aircraft as it flies, it creates two counter-rotating vortices. And as these vortices turn, they pull a lot of air around them, okay? And this air that's being pulled around them creates this smooth updraft within the vicinity of each vortex on each side. So in theory, if you follow if a follower aircraft or another aircraft is flying approximately, we say about 3 kilometers behind the leader aircraft and comes within this kind of smooth updraft, you can retrieve this lost energy from the leader aircraft. And ultimately, this is air that is an updraft, if you like, just like gliders, etc., are using thermals. Well, this is a smooth, steady flow of air vertically, which allows you to reduce your angle of attack of the follower aircraft, reducing your fuel setting, your engine setting, and therefore reducing fuel and corresponding emissions. So actually, there's been a lot of studies on this. I think even NASA performed some studies in the past. And in 2016 in Airbus, we actually flew an A350 aircraft behind an A380 at about 1.5 nautical miles, 3 kilometers longitudinal separation. And we found instantaneous fuel burn savings of over 10%, which really is huge in the aviation world. So what we did following this is we've launched a demonstrator project called Fellowfly. So Fellowfly, the name we chose really to think of this kind of fellowship, friendly collaboration between airlines, between ANSPs, between the industry globally, and I'll come to that in a minute. So the Fellowfly demonstrator will really set out to answer 3 key questions. So the first one is on a technical side, can we safely have a safe onboard solution to find and follow the wake of a leader aircraft? And in that sense, we did some technical feasibility flight trials this year, which I'll come on to on the next slide. But of course, operationally, as a lot of the people in the audience know very well, having an onboard solution is not sufficient. The technology isn't sufficient. You need a means as well to bring aircraft together operationally in order to execute fellow flight missions. So that means the ops control center of an airline. It means also air traffic management community. And this is very much an important part of this project as well. So in 2021, we plan operational feasibility flight trials with our partners. But of course, having a safe technical solution on board the aircraft and also having an operational solution still isn't sufficient. We need to ensure that we have a robust value chain for all of the stakeholders, for the airlines and the air traffic management as well. So in that sense, we're working with partners. And what we really do believe is that from a technology perspective, we could be targeting a controlled entry into service for oceanic operations around 2025. So the onboard solution, we have been working this year, in fact, on an onboard technical solution. And we actually did some flight testing end of July this year. We did that with two A350 flight test aircraft in airspace just off to the west of France. And you can actually see here in the little screenshot, you can see the aircraft quite close together. And it was a very exciting and very successful flight test campaign that was really very something that we're very proud of. So it was the first automatic tracking we had with a flight test solution. So this is not a fully certified, a fully solution that's ready to go into service tomorrow. It was the first flights we did with that. But what we showed is that in calm air, we could safely track the vortex using this solution. So of course, there's further feasibility testing that's required. And indeed, we're working on that as we speak for additional flight testing next year. Now, operationally, how would it work operationally? Well, we've been working with our partners on a safe concept of operations that we've been working with very intensely over the last few months. And we have a short video here that will just summarize a little bit the type of concept that we're referring to. So we'll just load the video. Hopefully, you'll be able to see it and hear it. So there we have kind of a very short summary of how we see this as coming into service. Now, this is very much a concept that, as you can see in the video, which is more adapted to oceanic traffic. So we are a demonstrator project, and what we're looking, as mentioned earlier, is to demonstrate the feasibility from a technical, from an operational, and also from a commercial perspective. Now, in order to be able to do that, we've joined forces with a number of airlines and ANSPs in the industry. So we're very proud to be working with SAS, French-B, Eurocontrol, NATS, and DSNA. And we also have two other ANSPs that have joined us recently that we will be announcing publicly. Coming back to the technology, so we really do see that the technology could be available around 2025, which is an ambitious time frame, and it really is important to be aware of this project so that we can plan rulemaking and ATM impacts, and also understand the time frame that would be needed to bring this to the skies. So the airline and ANSP partners were working really on the operational side and how this could really be brought together. We're coming up with a draft concept of operations for oceanic airspace, and we look forward to sharing that more publicly at some point next year. So really, coming to SESAR, how could SESAR help us? Well, once we've proven the feasibility on these on these fronts mentioned, well, there would be a need in order for us to work on a continental concept of operations. As you all know very well, the oceanic and the continental airspace is very different, and so that's something that could be an opportunity in the frame of SESAR 3. And finally, just to summarize, it's very important for me to highlight, as you all well know, that we can only bring this to the skies by having very much a federated cross-industry approach for all parties. So the 2021 live trial, well, I mentioned feasibility, and there's no better way of showing it's possible than to do it. And that's basically what we plan for next year, is to use 2 Airbus flight test aircraft, bring them into the Atlantic airspace, and do a live flight trial showing that our onboard technology works, showing that air traffic procedures in line with the concept of operations are possible, and showing ultimately the fuel savings, which is what this is all about. So this is a project which is very much focused on the environment, proving 5 to 10% trip fuel saving for follower aircraft in service. So just as a small conclusion, so we talk about wake energy retrieval. Some people have heard of the project under the name of formation flight. We like to avoid this term formation flight, as it does have connotations of fast jet military aircraft very close by with 5 meters between their wingtips, which is not at all what we're talking about here. We refer to wake energy retrieval because the aircraft are 3 kilometers apart longitudinally. Okay, so wake energy retrieval is what we're talking about. We're using the air upwash to lift a follower aircraft, so this is lost energy normally from a leader aircraft that we're retrieving, and 5 to 10% trip fuel saving on long haul flights is what we're targeting. In terms of the emissions targets, well, the corresponding 5 to 10% trip fuel saving on the follower aircraft also obviously applies to emissions, and so this is very much a project that we see as able to contribute to the reduction targets that the industry we've set ourselves. Collaboration with airlines, ATC, and regulators is absolutely essential. Again, we can bring the technology to the aircraft, but it's essential that we're working with ANSPs and with airlines and with ICAO and other industry bodies to enable this to come to the skies. And that terminates the presentation. Thank you very much for listening.
Thank you very much, Nick. That was really interesting.
Thank you.
You have quite a few questions there that you may want to take a look at.
I'll take a look at
So, then we're going to proceed with the Q&A, but we're going to go back to our first presenters.
Very much.
So maybe I can ask Florence and Max and Remus to come on stage, please. Thank you. So we've had, I saw you answer many questions. I kind of would like to go back on some of them, on some of the themes more than the specific questions. Maybe first to Florence, I would ask, we had a question about sectorization, and Max answered, well, for skyguide, it works the same sectors. So looking at the more holistic, let's say, R&D perspective, is it so everywhere, or sometimes do you foresee that when implementing free route, there is a need to redo the sectorization, so changes to sectors? I think you might be muted.
It's better now.
Perfect.
Okay. During the validation exercises, indeed, we did not change the sectorization, but we know that sectorization that was defined previously according to the ATS route network is no longer relevant in free route environment. And if we want to stick to the traffic flows, the best options will be to work with airspace reshuffling of the airspace in order to stick to the traffic flows and to the traffic, which could change from one day to another.
Okay.
So it's really a dynamic airspace configuration.
All right. So you foresee there's a dependency there with the dynamic airspace configuration.
Exactly.
Because
Exactly.
one day the free route can be, depending on the wind or something, that even the same between the same city pair, they can file on different routes. So it's not always the straight line. Would you say, so do they always file between a city pair the same line, or does it depend on the wind or other aspects?
Well, it's maybe it's rather a question for you, Max. It depends on it's everyday operations. It's not R&D anymore. What we thought during the R&D work was that depending on the winds, on the priorities for the companies, on the airspace capacity, the trajectories will not be the same. So really a need for dynamic airspace configuration. But maybe Max, you have more feedback on that matter.
Yeah, I think it's important to sort of define the difference between a simulated test environment where we are testing city pairs. We get a set of flight plans which we apply to the route structure, and then we apply the same, to be able to compare them, we apply them to the same airspace using a free route structure. But day-to-day operations are fundamentally different from this. I mean, one day you could have thunderstorms somewhere, so people are flight planning around the thunderstorms. One day you can have, as you mentioned, different winds. One day you can have industrial action in a country which causes people to file a different way. So the reality is that it is possible on any given day to have a flight between two cities going a different way. It's even possible to have within the same day different airspace users, different airlines using different routings to get there. I agree with what Florence says, that the future is a more dynamic sectorization to allow for the trajectories that you receive on the day. But in the first case, we have the sectors that we have today. And in addition, in these highly dense airspaces, we are not allowing a full free route. There are still some structural limitations to control the traffic flows, to maintain safety and to maintain complexity for the controllers as well. Obviously, future technological innovations will change that, but for the first implementations which are happening, within Europe at the moment, it's important to limit the size of the change, which is generally meaning that they're being implemented within the existing sector structure.
Thank you, Max. That was very clear. We had a few questions now that you mentioned safety, on how the safety is assessed and how it will be assessed in the implementation. What kind of metrics do you use to assess the safety? I guess there's a bunch of them.
Yeah, I mean, Florence answered, and perhaps it's useful for you to mention the safety report that was made within the SESAR project first, Florence, and then I'll talk about what we're doing at the implementation.
So during the safety project, we worked on a safety assessment. We performed a safety assessment following the SESAR methodology. So the objective was during workshops with ops experts to define some safety requirements, considering the concept and the novelty brought by the solution. And then these requirements were, we performed a check of the requirements, whether they were fulfilled or not, either during the validations exercises or by expert-based judgment, considering the concept of the solution itself. And so we produced a safety assessment document, a safety assessment report that is, as I said, available for the community to implement the solution. And I think it was used by Max teams to perform safety assessment at a skyguide level.
And I think what's important to understand is that there's a bunch of really useful information inside what was done, but it is skyguide specific because we participated to the simulations. So we had the SESAR questionnaires, but we also had some skyguide questionnaires, and realistically, using the sort of phraseology from the safety world, we can consider that the functional hazard assessment has been done. We know what we need to do to achieve a safe environment. We know, for example, that we need modifications to the skyguide FDP, and we need to be able to see the exact route. We know that we need some exit conflict detection. Without these, it's not safe for skyguide to implement the free route airspace. Then, what I need to do with my project team is just look at the differences between, that functional element and to look at the system safety aspects. So, for example, the simulations, so we're done in perfect environment, no military, no weather, no things like this. So we need to consider military activations. We need to consider, the focus was on the upper airspace, but we also need to consider how do we climb and descend all of the traffic to and from the terminal areas below this. So this is the sort of work that we're looking at inside my project with the safety department now, is analysing the system elements and what has changed there, and making sure within the safety workshops that we'll be conducting in the next months, how we assess these to make sure that they're okay.
Thank you very much. We'll proceed now to Remus, but he was here on stage and then he stepped out. I don't know, Remus, if you can come back in or you had a problem.
I'm back.
Welcome back.
Yeah,
Good to see you. I would like to ask you about if you see the result of the poll. It is overwhelmingly that collaboration is the main thing. So maybe you want to comment on that. Do you agree? Or was something that we're missing there?
Unfortunately, I don't see the results of the poll, so I was really interested in what people could say about. So indeed, the future ATM system is built around collaboration. So we speak about collaborative processes to be performed in coordination from the local up to the network level of planning and operation. So indeed, I fully agree with those telling that collaboration is a key enabler in building the future ATM system in an efficient manner. Why collaboration? Because collaboration means first exchange of information. Yeah, so sharing of information could lead to a better awareness, especially when it comes to the military operations, and then consequently a better integration of those requirements into the ATM system. Collaboration means also an exchange of information on the priorities that could drive the military mission, and also on the preferences of civil traffic, and to create the possibility to balance them throughout what we call a collaborative decision making. So in the end, yes, I fully agree, collaboration is very important.
Thank you very much. We're gonna now proceed with the next two speakers. So maybe I can ask you to step out, and then Sigrun and Nick, if you can come on stage, please.
Hello again.
Hello. Hello, Sigrun. You're muted. So
Yes.
yeah, great. I will start with Sigrun. We had various questions. One that piqued my interest was about the different types of aircraft. Mm-hmm. And you did say, well, it depends on the type of fuel. And this actually, I was wondering, what is which? I guess your project for the timing is focused on the, let's say, on the normal jet fuel. Do you have some ongoing work in other fuels, and like maybe even hydrogen aircraft? I've heard that they are problematic in terms of contrails as well.
Yeah, exactly. So let's start. I mean, the first thing is it's mainly the atmosphere who's driving. Okay, that's the first, let's say, first order effect, and then you have additionally a bit the geometry and the aircraft type, which is causing the question: how does a contrail form and how large it is? And then we come to the next order effects, and this is in fact when we come to fuel. So depending on the fuel you burn, I mean, let's go to the extreme thing. You are burning water, hydrogen. If you burn hydrogen, you will have much more water in your contrail, and you will change the composition, and you will have the mixing line, which will change. So the gradient of the mixing line will change. So there will be a different onset for the contrails. And this is the same if you have alternative fuels, because it's the hydrogen content of the fuel which determines the amount of water vapor produced during combustion. So in fact, there are kind of, it's a bit a second order effect. The dominant thing is, of course, the supersaturation of the atmosphere. This is why some days the sky is white and others it's not. But then these new fuels require additional investigation, and we are currently also investigating to make sure we know the answer. And there are a couple of scientific studies which have already explored, but not yet everything answered. Yeah.
Thank you very much. And specifically in your project, it's focused on the jet fuel, right?
Yes, current fuel. Let's say it's current fleet, current fuel, and we normally do a kind of typical. In fact, it's the typical energy content of the fuel that we are assuming, because there is a kind of empiric Schmidt-Appelman criteria. That's the Schmidt-Appelman criteria, which is determining it's the current ancient fleet. That's the status. Yes.
Thank you very much. And for Nick, there were many questions that were actually showing enthusiasm about the idea. What a great idea, which is really interesting. And then there were some questions asking about safety, and then another question about whether you had specific quantifications from the last flight trials of the savings, and maybe if you can expand on what do these savings depend on? Is it just how long your trip is, or are there other factors that would make you save so that you save more or less?
Sure. So firstly, needless to say, aviation industry safety is the first priority, and that very much holds for this project as well, of course. So what we're looking, as I mentioned, we're looking for a safe solution. If we determine that we can't have a safe solution, well, then clearly we will stop the demonstrator project and we won't proceed. Okay, firstly. So that's one of the things that we'll be really focusing on next year in our flight trials. The second point on the fuel savings we demonstrated. So I'm not going to give you specific numbers for the simple reason that it's actually not as simple as you might think, in fact, because aircraft performance is something that depends on many, many different factors. So simply saying that we had the 2 aircraft and this is what we saw isn't necessarily representative, which is why I've been talking about 5 to 10% trip fuel saving. It really depends on which aircraft you're flying behind. The higher the mass of the aircraft in front, the more powerful the updrafts that you're creating, and then the mass of the aircraft behind also influences that. And of course, you've got 2 aircraft flying together, so you need aircraft that are compatible with a similar max speed and with also an altitude which is also adapted again to the masses. Okay, so the mass of the aircraft determines the altitudes, depends which aircraft that can be paired together. So you can't pair every single aircraft together, and there are aircraft that don't fly at the same Mach, so therefore you wouldn't want to pair them together. Okay, but what I can say about the flight trials in July is that they were the fuel burn savings that we had were in line with our 5 to 10% modeling, and crucially they were in line with the modeling, which is good because it means that we have the right model. So the flight testing confirmed the predictions that we were expecting, that we've understood the physics, if you like. And that was very encouraging. And the third point, I think you might just remind me, Olivia, because I think I've forgotten it.
It was whether there were factors that would make you save more fuel or less fuel, but I think you also already answered when you said, well, it depends on the mass.
Exactly. So the mass, of course, but again, the longer you are in this wake energy retrieval mode, okay, where you're retrieving this lost energy, clearly the higher the percentage of the trip fuel, because generally airlines, we're talking about trip fuel, it's all nice saving 10% fuel instantaneously, but what they're really looking to do is to reduce the trip fuel. So the longer they're flying together in cruise, so this is something we're using cruise, the longer they're flying together, the greater the percentage overall. So therefore, yes, we're targeting long-haul travel. So the longer the sector, the heavier the aircraft in front, the better the fuel burn savings would be. And so this really is something that we know already. Yeah.
And then I'm going to ask a question that I don't think was asked, but I would really like to know. Would you foresee, so are the two pilots talking to each other, or are they in contact, let's say, because they're so close, or they're just in contact with air traffic control? This is a very question from a controller point of view.
It's something that we've really been focusing on in our discussions with our ANSP partners, of course. And as you saw in the video, well, a lot of people have been telling us, well, look, military operations, we already do this. A lot of people have been comparing with, again, formation flying, and this isn't really formation flying in the sense of what the physics of what we're looking to do and the environmental impact. But there are comparisons in terms of aircraft flying together in a reduced bubble, if you like. And so in that respect, what we've been hearing actually from a lot of industry partners is, well, look, I mean, we already do this in military operations, and yes, in military operations, it's the leader aircraft that's communicating with ATC, and then within the formation, they're talking together. So this is one thing that we're focusing on. We don't have the answers to all of our questions. Let me be clear on that. That's why we're here. If we had the answers to all of our questions, we wouldn't be a flight demonstrator. We would have already made the decision whether this made sense to industrialize or not. So we're still looking at some of those questions, and that's what we're working with our airline and ANSP partners on this concept of operations.
Thank you very much, Nick. So we've exactly reached our time. So thank you very much, everybody. We're going to close. We'll leave it here. It remains me to say just that I think Christmas is next week. I have just realized I forgot something, which is that Philip was going to give his closing remarks. So I apologize for that, and we're going to finish a little bit late so that Philip can talk to us now. Philip, can you come on stage, please? Welcome. I can't hear you, or maybe you haven't spoken yet. So while Philip sorts out his microphone, just let me tell you that Philip very recently joined the STU. He's our brand new Aviation Sustainability Program Manager. He has, like me, an operational background. He worked as a controller in France for 7 years before he joined Eurocontrol. And then he worked in the network manager in various roles. And then since 2016, he was seconded from Eurocontrol to the European Commission. And he was working in the aviation policy unit, and he was focusing precisely on the aspects of environmental policy. That is why he's completely in his domain here today. Philip, please. We can't hear you at all. Or maybe I can't hear you. I don't know if other people can.
No, I cannot hear him either. Okay, sounds like he's mute.
Can you maybe do a connectivity check, Philip?
Yeah.
Now, can you hear me now?
Perfect, yeah. Perfect. So now please go ahead.
Magic. So now it works. So thanks, Olivia. I thought you had forgotten me, but I was okay anyway. But okay, let's say a word. First of all, thanks to you to have led us through this very interesting journey of 3 webinars. You remember at the first webinar, I had expressed some views on what sustainability is and what is leading to. Climate impact mitigation is not as simple as just acting on the CO2 emissions. And it's clear now that we must consider non-CO2, like we've just seen now, the noise, the local air quality. And all the presentations from our partner in this webinar have clearly demonstrated, and we understand now that interdependencies and trade-off are going to be key driver on how, in a reflection on how and which ATM we want to see in the future. So I've been seeing the presentation and all the comment on the side. I just would like to make 2 rapid conclusions. First one, we can be very optimistic, I think. We can say that solution will be available. I'm convinced that on the side of the GU program, when looking at the potential of all the solution on environmental benefit, or if we look at the extent and the diversity of solution in all the section of the flight, we can be sure that there will be proposals that will address the need and match the particularities from the different stakeholders, which is important. We need naturally to consider and understand that this is research and development, and we will need to mature product, but with a few examples presented on the webinar, and we had many more that we could have shown, the problematic in these 4 areas that we need to work on will be addressed. So I'm very optimistic on this side with 2 main problematic. In fact, it's maybe we will have to look at reducing the life cycle of solution from R&D to implementation. And the second possible problematic is how to foster financing incentives for the one who will be moving first and leading the way as examples. The second conclusion we can have is all along this webinar, we have often seen as a comment about the solution we were presented that this has been already tested in the past, that we were not interesting enough. How much can we really impact environment with this? What about the capacity? What about the delay performance, etc.? So basically, at which cost are we prepared to move towards sustainability? Well, I think this we have to clearly understand that we must debate on that. The debate has to be on the table now. Mitigating the impact of aviation footprint, it's just not nice to have, it's business critical. This week, the Commission increased the pressure by raising the environmental target at the 2030 time scale, and DG Move published the Smart and Sustainable Mobility Strategy. And in it, it indicates that, I quote, overall, we must shift the existing paradigm of incremental change to fundamental transformation. I think that says it all. So our traditional focus we have in ATM should evolve toward looking at the trade-off between delay and sustainability. And we cannot give anymore a systematic priority to delay performance only. This will have, we will have to balance at operational decision time whenever possible, flying what could be, and this was mentioned in the webinar, a climate trajectory, and we challenge it with delay and capacity performance. It's certainly challengeable, but unavoidable. So next year, concretely, what's next? The SESAR GU will next year define what will be the 3rd generation of the GU program, and what will be concretely addressed in it. The strategic research and innovation agenda already frame at a high level the scope of what will be done, but it will be very interesting and challenging to enhance the catalog of solutions with new innovative and disruptive action and solution that will help us to move toward our objectives. We really need now to make the difference. Airline and airport are very much ahead. We have to catch the train, and so that by 2030, European skies can become the safest and certainly the most environmentally friendly sky to fly in Europe. Voilà, a very nice end of the year to everyone, and back to you, Olivia. Thank you.
Thank you very much, Philippe. So you did have a closing remarks. I apologize that we have no more time, and so I apologize for this 5 minutes, 7 minutes late that we are now. It just remains me to tell you thank you very much for attending this webinar. Please follow up on the SESAR GU website. We continue to have webinars and events, and we're going to continue to work on all these things. So the story does not end here. And Christmas is next year. Merry Christmas to everybody. Thank you.
Thank you. Bye-bye. Merry Christmas.